The next topic we're going to talk about is satellite motion. To start off with, talk about two different types of satellites, natural satellites and artificial satellites. Natural ones are celestial bodies that orbit one another, that orbit another body. And artificial satellites are objects placed into orbit by humans. Both are satellites. So, astronauts in the space shuttle are able to float as if the force of gravity isn't acting on them. Is it? Well, yes, the force of gravity is acting on them. Okay? The thing that is actually happening is that they're constantly falling. That constantly falling has to do with the fact that they're moving around the Earth in a circle, that parabolic motion. Let's talk about Newton's cannon. Let's talk about Newton's cannon for a second. What he hypothesized, I don't know if you guys talked about this last year, right? Is that you have the Earth here, and if we put a cannon on the Earth, right here, shot a cannonball. We shoot it at one speed. For a while, may fall down and come back here. Okay, shoot a little bit faster. Right, may fall down, come down somewhere over here. But we shoot it fast enough, we're gonna be able to put it in orbit, and it will continually fall, but it will never quite get to the Earth. Okay, so you keep just going around the Earth. So that's exactly what's happening to astronauts when they're in space. You can go back and look at our force balance dealing with centripetal motion and the universal law of gravity. Law of universal gravitation, from the first presentation. So, what is weightlessness? Well, it's a perception based on no reaction forces pushing on an object. Right? Perception based on no reaction forces pushing on an object. What causes the sensation of weightlessness? Well, we got a few different examples. For free fall, there's a thing called the Bonnet Comet. It's an airplane that follows parabolic paths through the sky to give its passengers momentary feelings of weightlessness. Right? So this is for free fall. Again, it's just falling. Okay. At the same rate as everything else around us. Surroundings, whatever you're in, maybe a roller coaster car, get a little bit of perceived weightlessness as well. What about orbital motion? Well, moving in a circle, really fast, obviously, as you fall. And what about deep space? Well, just a lack of gravity in general. Very, very weak gravity. So there's some things we can calculate here for satellites, right? Even before, with the period of satellite and the derivation location, we need a little bit more room. We had that force balance where the net force, right, causing centripetal motion is equal to the force of gravity. We solve for period here. The way we're going to do this, okay, is that we're going to substitute in the definition of centripetal acceleration where it's equal to 4 times pi squared times r all over t squared. When you do that, right? When you solve for t, rearrange this. There's some algebra. You look at t squared here. It's equal to 4 times pi squared r cubed over 3g times t squared on both sides. We end up with a formula for the orbital period of any satellite that's orbiting any other object being the square root of 4 pi squared times r cubed. Divided by 3g times. Yeah. Here. speed of a satellite, and with this example, we're doing the force balancing sets for centrifugal acceleration this time. We're going to use a different definition. Alright, so the little letters cancel out, and here we're going to substitute the centrifugal acceleration equal to v squared all over r. Alright, and we do that. We get this here. Okay, and we solve for v. You end up with what we had before, which is the same as the escape speed. Actually, no, excuse me, that's different than the escape speed. I'm sorry, completely different. Lastly, the acceleration. Okay, so here we got this, so v is equal to g and r. Last one is the acceleration of a satellite, right? And that's centrifugal acceleration, right? That we need it has to be equal to this rate at which it's falling, okay? And that's going to be our big G times big N over r squared, right? And get that from the force balance. Okay. So this problem here says we got to compare the motions of these two different satellites and the energies of both of them. So here, when we're closer, all right, just based on our orbital speed equation, since r is smaller, that's going to make b larger. So for the motion, right, A is moving faster than B. Therefore, A has more kinetic energy than B, right? And what we're going to say here, right, is that B has more negative potential energy, right, than A. Right, again, that really doesn't mean anything. We have to talk about a change in gravitational potential energy to have it be physically meaningful. So speaking of energy here, of orbiting satellites, all right, we define the gravitational potential energy, U is equal to G, big M times little m over R. Okay, kinetic energy we're going to define as this. All right. So what we have here is that the total energy, all right, we're going to get to that in a second. Actually, there's another way that I would like to define the kinetic energy, all right? So from our force balance, again, keep going back to this, we have our m v squared over r, that's sort of our definition for centrifugal acceleration. Go back to your notes from last year if you're rusty on that, or use your textbook. All right, the section on circular motion would be a good review for that. So what we're going to do here, all right, is I'm going to multiply both sides by r. Right, and left with m v squared is equal to big G, big N times little m over r. Right, and this left side is very close to kinetic energy. If I just multiply both sides by 1/2 here, then I should end up with kinetic energy. And so what I have here is another formulation for kinetic energy, and this is going to be very useful when we do our total energy calculations. Okay, so these are both equal to the kinetic energy. When I come back to where I was before here, right, I define the total energy here as obviously some kinetic plus gravitational potential. And we put that new definition in here for the kinetic. So it's going to be 1/2 big G, big N, little m over R, minus big G, big N, little m over R. So we see that the total energy is actually equal to negative the kinetic energy, right? Negative 1/2 big G, big M times little m over R. All right? So what we have here, you can cross this out, I can be doing comparisons here. We got the kinetic energy coming down here, all right? And so we have the total energy right there. Actually, that should look just the same, so let me draw that better. All right, so this is the total energy E and gravitational potential energy. That should come from like right here, something like that. All right, and that is our U. So actually, that looks a little bit confusing. E, whoops. E right there. There we go. Okay. Do some calculations. We got 15 200 kilogram satellite. All right, it's to be put into orbit around the Earth at an altitude of 200 kilometers. And calculate the gravitational potential energy with this equation right here. Again, R is going to be equal to this value. So the gravitational potential energy is negative 3.04 times 10 to the 11 joules. Therefore, the total energy is equal to 1/2. Actually, you know what? I think on the previous slide, you can go ahead. I think what I was referring to with this comparisons thing here is just to say that E total is equal to negative 1/2 gravitational potential. All right. Or no, just 1/2, not even that negative. Sorry. There we go. All right. So negative 1.52 times 10 to the 11 joules. We solve for V, square root of big G times big M, mass of the Earth divided by the radius here that we're going to be orbiting at. So it needs to be going at 7.79 times 10 to the third, or 7.79 kilometers.